Thank you, Alexander. I'm very excited to be here. Thank you, everyone, for being here. I'm going to talk about a recent result on size-free generalization bounds for ConvNets, and this is joint work with Phil Long. Recently, we've had substantial progress in theoretical analysis of generalization in deep learning, and I'm very excited that many of the authors that I've cited are actually here in this room, and the details of citations are all in the appendix of the slides. I couldn't write all the details in one slide. Yeah, so we've had a lot of progress, and something interesting that has been noted with roots in Peter's earlier results is that even if there are many parameters, the set of models computable by using the weights with a small magnitude is limited enough such that we can actually use induction. And that has been used in Bartlett et al. 2017 and Neishabur et al. 2018. Intuitively, when we start with the small weights and the algorithms that we usually use make small progress throughout training, and as we get closer to the optimal point, the steps become smaller and smaller, so we are essentially getting into small weights. And so there is tendency for the algorithms that we use to produce small weights, which is analyzed in detail as implicit bias of deep learning by Surya et al. And Tengu also has worked on it. What we are interested in is distance to initialization. There's been even more recent results on generalization bounds in terms of distance from initial setting of the weights instead of the size of the weights. And again, this has been used in Bartlett et al. In 2017 and Neishabur et al. 2019. One thing that is important to note is that small initial weights may promote vanishing gradients. So instead, it's advisable that we choose initial weights that maintain a strong but non-exploding signal as computation flows through the network. And this has been advised by many works. So what we know recently is that for a large network initialized this way, a variety of well-behaved functions can be found through training, where there has been actually a short distance traveling parameter space. So what the point I want to make is that the distance from initialization may be expected to be significantly smaller than the weight magnitude. Furthermore, there is theoretical reason to expect that as we get more and more over-parameterized, as the number of parameters increases, the distance from initialization decreases. What we are focusing on here is generalization band for ConvNets. As we all know, convolutional layers are used in all competitive deep neural network architectures that are applied to vision and image processing tasks. And the most influential generalization analysis in terms of distance to initialization so far have only focused on fully connected layers. Of course, we can think of convolution as in a reparametrization and think of it as a fully connected and then use all the earlier results. However, if we do that, we are missing an important property of convolution, which is weight tying. And intuitively, weight tying employed in the convolutional layer is constraining the set of possible functions computed by each layer. And this additional restriction is expected to aid generalization. So I hope so far I've convinced you that it's important to look into this thing. And in summary, this is the result we get. Our bounds are in terms of the training loss, the number of parameters, the Lipschitz constant of the loss, and the distance of the weights to initialization. And they are independent of the number of pixels in the input and the height and width of the hidden feature maps. And I want to emphasize that this is the first supervised learning bounds for deep convolutional networks that have this property. So let's recap what we mean by convolution. Of course, I know that this audience doesn't need this recap, but just to make sure we're all on the same page. So when we talk about convolution, we are talking about a discrete convolution, and this is linear combination of pixels applied locally. So this is your input. You have a kernel that moves around the input and generates the output at different locations. So of course, like any other linear operator, we can write convolution in terms of a matrix vector product. So here is an example. I have a 1D convolution. The upper part is the input, then the small vector is the kernel. If you think of this convolution in terms of a matrix vector product, this is the form of the matrix. Here I'm ignoring the edge effects. And this matrix corresponding to convolution is what we refer to as operator matrix. And the notation we use is op of k, where k is your kernel. Of course, we have more complicated settings. You can have a 2-dimensional single-channel convolution. And if k is your kernel, then the operator matrix corresponding to it can be calculated directly by some form of circulant analysis. And again, we refer to it as op of k. We have extensively analyzed convolution for 2D case and multi-channel convolution in our earlier results. This is the paper we just had at Eichler. So what we did was that we analyzed this mathematically, and we proposed a simple and efficient algorithm to find the full spectrum of the convolution. And we proposed upper bounds for the spectral norm of these convolutions. And also we proposed an algorithm to project the convolutional layer into a set of bounded operator norm bar, which can be extended into 3D multi-channel convolution and so on. So the reason for mentioning is this, that in the rest of the talk, I'll be talking a lot about the spectral norm of the operator matrix corresponding to convolution. And I want to mention that whenever I say that, please note that we already have a good algorithm. It's simple and efficient to find that. So let's get started. I will start with a basic setting. Let's say I have an L-layer convolutional network. You have the usual zero padding and pooling. And the activation functions that we have in the network are one Lipschitz and non-expansive. For example, we can have ReLU or tanh. You have a tensor input which has C channels. And if you vectorize your input and you look at the L2 norm of that, it's bounded by 1. The number of channels throughout the network is C. And you have L kernels, and the dimension of your kernels are k by k times c by c. So if you think of total number of parameters, essentially we have L, k squared, c squared, total number of parameters. The loss function we have, we assume it's lambda Lipschitz for all the value of labels. A famous example of this is margin loss, where if you have a margin loss with margin of lambda, it's 1 over lambda Lipschitz. Another assumption we make is that the operator matrix related to kernels at initialization, its spectral norm is 1. Please take a look at this value that I've mentioned here. So we define the distance to initialization here as sum over all the layers of the difference of the operator matrix to its initialization and the spectral norm of that. Note the difference between this value and the earlier results where the distance earlier works looked at was product over all the layers. Here we are looking at distance to initialization and sum over all the layers. And the set of functions we are interested in is that the set of function where this distance to initialization defined this way is bounded by some value beta. So what we prove is that in this setting, with high probability, the difference between expected error and empirical error is bounded by this value, which is linear in terms of number of parameters, linear in terms of the upper bound on the distance to initialization, and has logarithmic dependence to lambda, which is the Lipschitz constant corresponding to the loss function that you have. Also, as there has been discussions about interpolations. As much as interpolation is interesting, what we see in practice is that when we are optimizing for a good test error, the value of the empirical loss is not 0. So this case is still interesting for us to understand further. Now, let me get a little bit into the high-level idea behind how we prove this. In order to say that, let's recap on 2 definitions. One is the definition of full norm. We are saying is a norm over R to the D is full if its unit ball has positive volume. Another definition we need is a definition of Lipschitz parametrized models. So let G be a set of functions with a common domain Z. We say that G is B and D Lipschitz parametrized, where D is the dimension and B is the Lipschitz constant. If there is a full norm on R over D, where any mapping from the unit ball with respect to this norm in R, D to G is such that for all theta and theta prime, where their L2 norm is bounded by 1, if we look at the difference between this mapping of phi over theta versus mapping of phi over theta prime, this is bounded by some value B, difference between theta and theta prime. And this definition is the core idea behind what I'm going to talk about. So the most important lemma that we use for proving our results is this lemma, where it talks about this, that if you have a set of G of functions from Z to some bounded interval 0 and M, and this set of functions is B and D Lipschitz parametrized, then for any eta, there exists some C such that if you have large enough number of samples, with high probability, you have this difference, you have this bound and difference between expected and empirical risk, which is linear in terms of upper bound and loss, and linear in terms of dimension, and has logarithmic dependence to B, which is your Lipschitz constant. And what we do is that, given that we have this lemma, what we do is that we show that the set of loss functions over this set that we talked about is beta, lambda, e to the beta, and W Lipschitz parametrized. Just as a reminder, beta is the upper bound on the distance to initialization, lambda is your Lipschitz constant corresponding to loss, and W is the number of parameters you have. So if we put this together, essentially we are done, and we're able to prove our results. If you're eager to know more, a little bit more, we can dig further. So where does that lemma come from? The first part is actually old news. It's all the way back from Vapnik and Chervonenkis from 1971, and Vapnik and Pollard. What is new, relatively new, not in deep learning era new, is this result from Gina and Guyot from 2001. And this is interesting, and this is something that we hadn't been used in earlier results. And the secret behind this really nice bound, which has logarithmic dependence on Lipschitz constant and linear dependence to dimension, is that, of course, we all use covering bounds, but when they use covering bounds of the form B over beta epsilon to the D, they paid particular attention to the dependence of resulting generalization bound over B to B. Whereas earlier results, they were only thinking of B as a constant, and then they ignored this relationship. So what is left for me to show you is that how do we find this Lipschitz constant corresponding to the set of functions that I defined. So as usual, what we do is that we want to see if the parameter changes, what happens in the loss in terms of parameters. Let's start with a simple case where only when you have two networks and only the parameters in one layer changes. So as I mentioned, we assume that our loss is lambda Lipschitz with respect to its first argument. So if we want to bound the difference in loss, it's enough for us to bound the differences in function and then multiply it by lambda. How do we bound the difference in the function? What we think of is that I'm saying only one layer parameter has changed. Let me call that layer J. And let me split the function of the neural network in 3 steps. So G-up is from the input to the network all the way to before the layer that I've changed. And then I have the function and the layer that is changed. And then I have the rest of the function that I call it G of down. So let me call U to be G up of X. By the assumption we had that the L2 norm of input is bounded by 1, and also our nonlinearities have a Lipschitz constant of 1, it's easy to show that U is upper bounded by product of the operator norm of operator matrix of different kernels all the way up to level J. Now, if I want to look at it as a whole, essentially what we have is this difference. If you use the usual norm analysis, U comes out, and for the rest of the layers after J, you have similar products. So it becomes product over all the other layers. And then for the layers that is changed, we have a spectral norm of difference between operator matrix corresponding to this kernel that is changed. So the other assumption we had was that initialization, the spectral norm of operator matrix of all of these is bounded by 1. So we can write this in terms of k minus its initialization plus initialization. And we know the difference in initialization is bounded for each layer by bi. So this is what we get. Now, what we know, so this is what we had from last page. I put everything back in terms of loss and brought in lambda. So what we know is that the sum of the distance to initialization for all these layers is beta. So if I want to maximize product of 1 plus beta I, what I do is that I set all the beta i's equal to beta over L. So this is what I get in the second line. And then we know that 1 plus beta over L to the L is upper bounded by e to the beta. So we're done, essentially. Now, this was the case where I only changed the parameters in one layer. If we want to look at difference between theta and all the parameters being changed, we want to look at all the layers. And in order to analyze that, we look at the case where we change one layer at a time and we use triangle inequality. And this is it. We are done. We proved what is our Lipschitz constant corresponding to our set of functions. So we proved that the loss functions corresponding to the set of function is beta, lambda, e to the beta, and w Lipschitz parametrized. Now, if you put it back into the lemma that I showed from Vapnik and Guinet and Guyot, essentially you get the results that we have. Any questions so far?
The result in it, very high level, it's reminiscence of the Park-based bounds. That you have a bound generalization depends on the difference between your prior and your posterior. And here it is kind of the distance between your initial weights and the weights of the function that you try to estimate.
We used that actually examine this in our DNNS 2017 paper, like the distance of initialization in fact-based bounds.
Okay. So one question that might arise is that we are analyzing the same similar things to Bartlett et al. 2017. And so the question is that how do they compare? So in order to be able to do this comparison, we consider convolution as a fully connected network. And we look at high probability bounds in terms of the different generalization gap or difference between expected and empirical risk. All the details are in the paper. Here I'm going to talk about a specific case where you look at the case where initialization computes identity. And for all the layers, the value of your kernel is the initial value plus epsilon added to all the entries. Then this is what happens. Our bound simplifies to the line above. And Bartlett et al. 2017 bounds is the lower line. And you can see that in this scenario, the new bound is independent of D, which is what we promised initially. And also it grows more slowly with lambda, number of channels, and depth. So let's talk about a more general setting. Let's remove some of these assumptions and make it closer to what we have in practice. Again, you have zero padding, you have pooling, your activations are non-expansive. You can have L sub C convolutional layers, and you can have L sub F fully connected layers. So your network has both fully connected and convolutional layers. Your input is a tensor, and we're assuming that the vectorized version of the input has some upper bound chi. And your output is a tensor itself. And of course, we're not making any assumptions on the number of channels in different convolutional layers. It can be anything. But still we make this assumption, which holds in practice, that your loss is lambda Lipschitz, and also the loss at all these values that you are estimating for your network it's between 0 and some value m. Here we loosen up the assumption we had on the initialization. So essentially, a spectral norm of the operator matrix corresponding to your initial kernel can be upper bounded by some value 1 plus nu. So it's a looser assumption compared to the initial one we had. And also, for all the fully connected layers, their initial spectral norm is bounded, again, by some value 1 plus nu. The notation we use here, so we use VI to refer to weights for the fully connected layers, and theta is all our set of parameters, which means the kernels corresponding to convolutions and the V's corresponding to fully connected layers. So your depth is essentially L sub C plus L sub F. The distance to initialization that we look at in this case is that for all the convolutional layer, we take sum over all of them, the distance to initialization of operator matrix in a spectral norm meaning, and sum over all the fully connected layers, difference of weights, fully connected weights to their initialization, and the spectral norm of that. And we are interested in set of functions where the distance to initialization defined this way is bounded by some value beta. And we are able to prove these results. So this result holds with high probability, and the difference between expected and empirical risk is bounded by this value, which is linear in terms of upper bound on the loss function, linear in terms of number of parameters, linear in terms of beta, which is something really interesting, linear in terms of depth of the network, and also has logarithmic dependency between with lambda and upper bound on size of your input. So one thing I want to mention is that in our earlier paper, in our iClear paper, we showed that the spectral norm of the distance between any two kernels can be essentially operator matrix corresponding to kernels. So the spectral norm of operator matrix corresponding to two different kernels can be upper bounded if we vectorize those kernels and look at the L1 value of this difference. So the same bounds can be reached if we replace our definition of set of functions and instead of using a spectral norm, we use L1 norm. So if you like to use L1 norms, you can get exact same results. Another thing that I want to mention is that the bounds that we proposed holds uniformly for models that are all at the distance beta from initialization, but this can be modified using standard techniques to get non-uniform bound as a function of distance itself. So let's do another comparison. Now that we have results that directly hold for fully connected networks, let's compare again with bounds of Bartlett et al. 2017. Here we are taking away the convolution. We are comparing two networks that have all fully connected layers and they're deep. So we are saying that each hidden layer has big D components and D classes, where D is CD squared, C is number of channels, and D is the dimension of the input. And for all of them, we initialize them at identity, and the value of each layer is I plus H over root D, where D is a Hadamard matrix. Now, it's easy, given these values, to compute the spectral norms. So spectral norm of each V is equal to 2, and the distance to initialization spectral norm is 1. And the 2-1 norm used in Bartlett et al. Distance to initialization is equal to D. Now, if we rewrite all those bounds, the top one is the bound that we get, and the lower part is the bound from Bartlett et al. And we can see we have linear dependency with depth, whereas earlier result has exponential dependency with depth. So let's switch gears and talk about experiments. If there's any questions about theory socket.
Yeah, so your generalization, the bound is linear in the number of parameters, right?
Yes.
So how does it compare to kind of straightforward bounds that are linear in the number of parameters? Like VC dimension.
Like VC bounds.
Yeah, like.
VC dimension-based bounds are also linear in number of parameters.
Yeah, so what's the difference?
So the
there are a lot more factors here, but that's not necessarily a good thing.
So one thing that is new that we are seeing is that the terms that we have in terms of distance to initialization, and as I show in the experiments, and it has been something that more recently people have been looking at, is that how distance to initialization changes and how it can be used to predict generalization.
So if you make your network larger, I assume you computed the bound, you can see how it behaves when you make a network larger. So things like the distance, even though the number of parameters is going up, because the distance is going down, then overall your bound's going to go down.
So
that could be one difference.
yes, so that's something that we'll see in the experiments.
So it is going to happen.
Yeah, let's go over the experiments. And if there's any experiments that you were asking for and we haven't done it, then we can talk about that too. Okay, so here's the setting. We have a VGG style 10-layer all convolutional model. We have a CFAR10 data set. We are using dropout and the usual exponential learning rate schedule. What we do is that we repeatedly train the same network for different values of batch size and initial learning, so we have a bunch of trained networks. And I'm going to refer to generalization gap many times for the slides, for the rest of the slides. So just a reminder, generalization gap is what we mean by difference between train and test error. So let's take a look. So here is generalization gap as a function of total number of parameters times distance to initialization. And each of these dots is a generalization gap for one of the networks that we train. And we can see we can see the correlation between this value that we are proposing and the generalization gap itself. So we did further analysis. Let's look at generalization gap as a function of W, which is total number of parameters. So what I did here is that I increased the total number of parameters by keeping the depth fixed, but increasing the width of the network. And as we can see, as the network becomes more and more overparameterized, the generalization gap remains almost flat. Another thing that we looked at is that
not predicted by your theoretical bounds, right?
So what is predicted by our theoretical bounds is the first plot. But then we dig further to look into what's going to happen. Yes? So the other thing that we look at is to look at distance to initialization as a function of total number of parameters. The plot on the right is looking at mean and error bar for this distance to initialization, and the other one is showing the median. And as we can see, as we increase the number of parameters, what happens is that the value of distance to initialization is dropping. Another thing that we experimented with relates to role of input size. So earlier results, the generalization bound depended on the input size, but we came up with an analysis that is independent of the role of input size because we thought intuitively that should be the case. So, but we wanted to also check our intuition with experiment. So what we did was that, so CFAR10, as we all know, is 32 by 32 images. We downsampled CFAR10 images from 32 to 32 to 16 to 16. And then we did everything all over again. So we trained all our networks, and we looked at the value of generalization gap. So this graph is the histogram of generalization gap of this 10-layer all-conv model that we had. The green shows the values for 32 by 32 images, and the red shows the values for 16 by 16 images. And as we can see, the support is the same. So this graph shows us that the generalization gap does not really depend on input size, and this is something that our bounds had captured.
What is the x-axis and what's the y-axis?
So this is just a histogram. So the y-axis is the number of times that value happened in the number of networks that we trained, and the x-axis is the values of the generalization gap that we observed. Yeah, so this is something that our bounds captured. Yes?
I guess we can go to slide 5. So
Sure.
did you use the regularization here, like weight decay?
So we did not use weight decay here. We only used dropout.
Oh, only dropout.
Yes.
And do you know what happens with weight decay?
I haven't tried that, but we'll try. We can try it. And I want to emphasize that there was no batch, no.
And also, sorry, another
Sure.
question for the slide after. So this histogram is a histogram of the generalization of different random seeds, right? Across
Different random seeds. So what is the same is the network architecture is the same, and the hyperparameters are tried over a set of number of hyperparameters. For example, what we played with was batch size, 32, 64, and 128. And the other thing was the learning rate schedule is the same, but the initial learning rate we swept over a different number of values.
Oh, so they are not over random seed, they are over different configurations.
So the network is the same, the hyperparameters at initialization are different. Sure. Yes?
So why is it the case that the 16 by 16 has a smaller generalization gap? Because it seems that the red curves have smaller generalization gap, which is kind of counterintuitive.
So essentially what happens is that when you make the input smaller, your train and test error both become, train and test accuracy both becomes low. And
So
maybe that's why it's more concentrated.
It's 16 by 16? So when you're reporting the x-axis, they're not, the 16 by 16 is in comparison with the baseline, it's 16 by 16. Is that how you
So basically it's the difference between train and test error. So what happens is that, so that's what we mean by generalization gap. So what happens is that when you make the size smaller, the accuracy for both train and test drops.
It's not the same comparison.
What do you mean it's not?
I understand what you mean.
Oh, okay. Yes?
I guess there are some recent papers that shows that if you scale up the resolution, the generalization becomes better. And there's other actual ways to, if you need to scale up everything.
Right, right. So yeah, so basically here we did not scale up everything. We were mostly interested in saying, okay, let me fix the network architecture and look at what things changes. If we really zoom in and make this dimension of the input way bigger, then I think that's the regime that we haven't really run experiments on it. We haven't really looked into details of those. Because if you make it really zoom in, then architecture also needs to change. So in conclusion, we provided the first size-free generalization bounds for deep CNN models. I want to emphasize that our analysis applies to practical architectures. You can change your activation functions and pooling operators to have a larger Lipschitz constant that can be directly plugged into our analysis. And also, many variants of our bounds are possible. So what we chose in the different variants that we could show is that the ones that were relatively simple and interpretable. But if you want to really dig into the details and come up with more detailed analysis, they're actually possible and they're completely doable given our analysis. You can even look at bounds in terms of Lipschitz constant of subnetworks that are bounded above by epsilon e to the beta, or you can, so when I showed the Lipschitz constant, I showed all these loosening up of the bounds that we did, but you can essentially not loosening up and get additional results. Again, we were aiming for simplicity and interpretability. And for future works, one thing we want to do is that we want to use the insights that we learn to use design regularizers for improving training and generalization in practical models. The paper is available on arXiv. Thank you all for listening.
So the VAPNet result, that requires bound 0-1 bounded loss function? Or because the generalization result that was the core of it was from that VAPNet?
Would you mind speaking louder? I don't hear you well, sorry.
The VAPNet paper was the core of the generalization result?
The first part, yes.
What were the assumptions on the loss function?
Sure. So essentially, the loss function, the most important thing we need on the assumption on the loss function that is bounded in some domain, and also it's lambda Lipschitz as a function of y, which is the output.
So does the method work when you have unbounded loss?
This is where it works, yeah.
That works for unbounded loss.
This works for bounded loss.
Any other questions? Okay, so now it's time to party. Hopefully there is reception either outside here where we can mingle a bit, talk about all the cool results that we've seen and plan even better ones. So yeah, and see you tomorrow.